All right, we're going to talk about rational functions, and I'll show you a picture in a little bit, but this is where we get into asymptotes. So we get into things that the little dashed lines where the function gets really close to it but doesn't cross. Vertical asymptotes are brick walls, you don't cross them. Horizontal are a suggestion, sometimes you cross those. So like this guy right here, you know, he's crossing that horizontal asymptote because it's just a suggestion for him. These two, it is, you know, it's there for them. So we're going to get graphs like these, all right? And so let me pause for a second and I'll kind of go to what we're doing here. All right, so the reason you're going to get these dash lines that kind of hem things in a little bit is because dividing by zero is a big no-no in math. All right, so this would be a vertical asymptote. So whatever causes zero is 1, okay? And that would be a vertical asymptote. All right, so let's think of the steps of doing this. First is you are going to factor, because something that can be hidden that can mess everything up is a hole. And so after you factor, the first thing you are always going to look for is, do any of the factors cancel? If they do, you have a hole. All right, so let me give you an example. So we have x squared plus 3x plus 2 over x minus 5. Okay, so if I factor this, that's going to be x plus 2 and x plus 1, because my loopies would give me a 3. All right, so if I do that, notice none of these factors as a chunk, none of them cancel. So I have no holes. All right. So there's none. That's great. Okay. Step number 2 is we're going to look for vertical asymptotes. And that's because this is dealing with input. So input is your x values. Okay. So we're going to look down here because that's the only thing that can cause problems. We don't care about the numerator. What causes an issue here? And again, you look after you look for holes, because holes might change your function. So x equals 5. Causes 0, okay, because if you set that equal to 0 and solve it. So there's going to be a brick wall at 5, where if you graph this function, it is not going to cross that, okay? It can't. All right, next, we're going to look for horizontal. Now, horizontal could also include maybe a slant asymptote, or what we call oblique, or even a parabolic, where, you know, so it doesn't always have to be vertical and horizontal. You could have an asymptote that literally looks like a parabola and it hems in the graph that way. Okay, so it can be a wide variety of things. All right, so I'm going to go back to our beginning. So it was x squared plus 3x plus 2. Notice when I just look at my leading coefficients, I get x. X is a function. It is going to have a linear asymptote or a slant or an oblique. If I had x cubed over x, that would be x squared. That says, hey, guess what? You're going to get a parabola asymptote. If you have, say, x to the 6th over x, we don't mess with x to the 5th, you know, asymptote. So that would be like none, okay? But you do have to check. So, and the reason we only care about the leading coefficients is we care about that behavior because say someone says, hey, what's your car worth? And I have a quarter in my little cubby for Aldi. I don't say my car's worth $10,000.25 because there's a quarter sticking in there, right? It's just 10,000. The quarter is minimal. So if you know, have a huge number for X, this other stuff is just minimal, doesn't do anything, okay? All right, but this guy is going to have a slant or oblique, and the way you're going to find that is we're going to do long. All right, sorry about that. I had to cut that off. So, all right, so let's look here. So when I do long division, you match. So x, distribute, x squared minus 5x. Do the opposite, because you're subtracting 8x and bring down. Match, I need an 8, so positive 8. Distribute 8x minus 40, do the opposite, and then bring down. But again, I would quit as soon as I get the 8. The remainder means nothing. So this equation right here, y equals x plus 8, that is going to be my slant, okay? So we know, what do we say? I think we said we had a vertical at what, 5? 1, 2, 3, 4, 5 there. So if I go, you know, 8 up here and then slope of 1, you're going to have another asymptote. And I'm not paying attention to where they're going to cross, but you're going to have a line asymptote, a linear asymptote right there. Okay, and your graphs are going to do two things, you know, around that guy. Okay. All right, let's do another one. And again, I'll try to summarize at the end some general rules. All right, I just want to do a couple weird ones first so we can kind of get those out of the way. All right, step number 1, okay, factor. Okay, so perfect square minus perfect square. So you get that all over, and that's already factored. That is my factor. Okay, step number 1, we look for holes. There is a hole. Do you see how these cancel? Okay, so when you get a hole, yes, there is one, you get a point, which means you have an input and an output, where this graph is a hole, like it's just not defined there. And then you also create a new function. So my new function is actually looks like that. So it doesn't even look like a rational function because the denominator cancels. Okay, so where's the hole? What causes 0? 1. And then you sub 1 into the new function that you get when these guys cancel. So 1 plus 1 is 2. Okay, all right, so there's going to be a hole. So I'm going to go to 1, 2, and put a hole. Okay. Now let's look for vertical. Well, now we're going to look at our new function because the old is gone. Okay, we have a new guy in town because these guys canceled. There was a hole. This is really what we're looking at. There's no more denominator. So there's none of these guys, okay, because, you know, and there's none of the horizontal either because I don't even have anything that kind of looks like a rational function. I mean, I really do, but not my new function. My new function looks like a line, okay? And so if you sub in 0, you get 1. If you sub in -1, you get 0. And so this thing is a line. So this, if you graph this on decimals, it's going to look like this. And if you trace it, you're going to see that there's a hole at 1, 2. If you trace it to 1, 2, it's going to say 1, and then it's going to say undefined, okay? So the holes can be tricky because you might think it has all these asymptotes and all this crazy stuff going on, and it really has a hole. Now, I'm going to pause. It can have a hole and asymptotes. So let me show you an example. I'm going to go back to one of those pictures. Okay, here's an example of a function. You can see there's vertical asymptotes, horizontal, and a hole. So those can all happen. Okay, I might not get to it in this video, but that can definitely happen. All right. All right, so let's go through the process of this. I'm going to factor first. 3 only has 3 and 1. It's prime. I want the negative to be on the 3 because I want more negatives, so I get a -2x. So -3x, I do my little loopies. Here, what are the factors of 24? Remember, usually if they're close together, they work. And notice 6 and 4 give you a difference of 2. You want a +2. So I want my 6x on the positive loopy there for that loopy. All right. Step number 1, do I have any holes? Because that's going to create a totally new function, right? It's going to look the same as this, except it's going to have a hole because this guy has a hole. All right, nothing cancels, so no. Okay, vertical asymptotes. This is dealing with input. So whatever causes 0 down here, x equals -6 causes 0, x equals +4. So I know I'm going to have an asymptote at a -6 and a +4, right? Okay. Horizontal, and those are brick walls, cannot cross. This deals with output. Okay, so we haven't really done much with this, okay, because we've done the weird ones. I look at my leading coefficients because, again, 1,000,000 squared and 1,000,000 squared, this stuff isn't going to matter much. But notice that simplifies to 1. Those would cancel. So y equals 1 is going to be my horizontal asymptote, and my graph is going to do things around those asymptotes, okay? And the horizontal one is a suggestion, meaning things can cross it if they have to. All right, let's generalize this. All right, I'm going to pause for a second, and then I'm going to kind of write down, you know, what I'm thinking here, and then we'll talk about it. Okay, step number 1, you look for a hole. So say this is factored. Notice these are identical. You cancel them. Your new function is going to be the 4 parts that are left, but you're going to have a hole at whatever canceled, -2, and whatever you have over here, you'd have to sub a -2 in. So you would have to take those x values, sub a -2 in to see what the output is. Okay, so sub in a -2, sub in a -2, sub in -2, sub in -2, and see what that is. Okay, and you can get the output. So what is that? We have a -1, sub in a -2, what is it? -5, sub in a -2, that's a +2, sub in a -2, I think that's a -3. So 5, +5 over a -6, so -5, 6, I think. I did that quick. If I screwed up, please email me and fix it. All right, let's look at the vertical. The vertical are dealing with input. So you look at your new function because these guys are gone. That's your whole. So cos of 0, cos of 0, those are your two vertical. Those are brick walls. All right, now horizontal. In this case, this is what I have left. All right, so what I would do is if I multiply this out, I would get blah, 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 and I would get x squared with a bunch of stuff. Again, I only care about the leading coefficients. These cancel. And so y equals 1 is my horizontal asymptote, okay? And that's a suggestion. All right, now let's look at in general. If your powers match, and this is just dealing with horizontal, and assuming you have no holes, okay? This is just, you have no holes, and you know, this is what we're dealing with. So if you have no holes, you look at the leading coefficients. If they match, they're going to cancel, and in this case, the x squareds cancel, you get y equals 8. That is going to be your horizontal. Okay, going horizontally. Here, same things. Leading coefficients, the 7 cancels, so does x squared, y equals 1. Okay, next scenario is it could have a higher power in the denominator. Now, this is where we get into the idea of a limit. Ignore the other stuff, leading coefficients. If I shove in a million, 3 times a million, and divide by 4 times a million squared, I am dividing by a huge number. And so that's going to go to 0. Okay. And again, these are like my Aldi quarter. Don't matter. So if you have, as x gets huge, this is going to be 3 times whatever, a million, trillion, doesn't matter. But this is a million or trillion squared times 4. So a number divided by a huge number, this is going to go to 0. Okay. So your horizontal asymptote is going to be the x-axis. All right. Now, let's look at what if we have a higher power in the numerator. That's the one where we have some work. I'm going to pause and we'll talk about that. Okay, if you have a higher power in the numerator, this is when you can get slants, you can get linear asymptotes, parabolas, things like that. Okay, if it's this, and again, we're kind of thinking of a limit, this is x to the 4th power. We are not worrying about 4th asymptotes that are weird or 5th or anything like that. So again, if you put a million to the 5th divided by that, it's kind of like it's going off to infinity, like there isn't one. Okay, so if it's something like this that doesn't equal a linear thing or a quadratic, we're just going to say there is none. Okay, there is none. We're not worrying about it. So if this is to the 50th power and this is to the 20th, that is a 30th power. We don't care. Okay, now this one, if we look at the leading coefficients, notice that is a line. Right? That gives you a line. So if these cancel and give you a line, then you have a slant or a linear. And again, I've been painting my front doors, so my hands are black on it. Here, if you look at the leading coefficients, that gives you x squared. That's a parabola, okay, asymptote. All right, I'm going to do long division on both of these so that you can see what those asymptotes are. And if I have time, I'll try to graph them too. But I'm going to pause and do that long division and then talk about it and then hopefully show you a graph so you can see what it looks like. Okay, here I did long division. So I matched, distribute, opposite, bring down, match, distribute, opposite, bring down, match. And then I don't finish it because the remainder doesn't matter. This one's pretty because of this is x plus 7. You could do synthetic division, but make sure you use -7 because with synthetic division, you always use the root, not the factor. All right, I'm going to graph this so you guys can see this. So this is your parabolic asymptote. Okay, let me go to the graph. All right, when you first look at this, you might be like, I don't see an asymptote. Okay, we need to, we need to go out here so we can see what's going on. Ah, there you go. All right, it's kind of hard to see, but this parabola, which is your green, is an asymptote for this guy. Do you see that? He's hedging him in. And this guy, the blue, is your function. It's kind of weird, but yeah. So from a distance, it doesn't look, you got to get close to see it. Now, it looks like this guy crosses, which again, it's a suggestion, right? You know, but it might be just an asymptote for this side. This one looks like it might cross. I'd have to plug some numbers in to see. All right, I'm going to go back to the other one. All right, sorry, I had to edit a little bit. All right, I did long division. Here's the graph. You can see the line, the slant right here. This one looks like he crosses eventually. So, but it kind of guides it. And then over here, it might be a complete asymptote. I'd have to plug in numbers to see. And then we have this shape. All right. Now, let me show you the math for it. All right, I could not do synthetic division because it's x squared, but I did long division, and this is